Hello everyone. So in this video we will talk about some numerical problems on Newton's law of viscosity, as we have covered the basic introduction part of fluid mechanics in the previous videos. So we will cover three numerical problems on Newton's law of viscosity. The first one we will discuss is a cylindrical rod weighing 50 newtons having 10 centimeter diameter and 100 centimeter length is placed inside a fixed pipe of diameter 10.06 centimeter, which is lubricated by a Newtonian fluid. The cylindrical rod slides due to self-weight by 100 centimeter in the pipe that deaccelerates at 0.5 meter per second square when the speed was 4 meter per second. So what we have to do, we have to calculate the viscosity of the lubricating oil and viscous resistance force. In the second part, after the same rod is initially at rest, if since it is moving down and when it will come to rest, what will happen? The rod is made to rotate at 2500 rpm. So we have to calculate the frictional torque required to rotate the cylindrical rod and the corresponding power loss we have to calculate. So frictional torque we have to find out T, and power loss we have to find out. So first of all, we have to draw the diagram for this problem. So this is the case wherein you can see we have a cylindrical rod, cylindrical pipe in which we have a cylindrical rod of diameter 10 centimeters. So this gray color is a rod which is moving down with some velocity 4 meter per second, and it is deaccelerating. And that's why the negative sign is over here, minus 0.5 meter per second square, and the weight of the rod is 50 newtons. So the lubricating oil is there, lubricating fluid is there, which is a Newtonian fluid. So it certainly means that we will use Newton's law of viscosity. So in the given conditions, we have the weight 50 Newton, diameter of the rod 10 centimeter, fluid thickness which we denote will be y, it will be 0.3 centimeters, 0.03 centimeters, velocity and acceleration are given. So what we have to do, we have to calculate the dynamic viscosity first in the first case, and resisting force in the first case, and torque and power loss in the second and third case. So we have to find out all these values. Also we have to calculate along with this the power. Okay, power we have to calculate over here. Okay, so what we will use, we will use a Newton's law of viscosity, since we know that this fluid is a Newtonian fluid and the layer thickness is 0.03 centimeters. So we'll move towards the first part. So in the first part, by using the Newton's law of viscosity, you know that tau is equals to mu du by dy. So tau is equals to mu du by dy. If I will write this tau in terms of the force, okay, the force will be given by mu u by t, and since tau is equals to F by A, so A will be area which will be the lateral surface area of the cylindrical rod, because here you can see it is a two-dimensional figure, but it is certainly a three-dimensional rod. You know that the diameter is 10 centimeters, so the lateral area of this rod is pi dl. So since the rod is coming down with some weight and with some velocity, so there will be a shear force which will be developed over here, which will be denoted by Fs. So this shear force will be developed along the circumference of the rod. It will be on this side also. Okay. So we have to calculate this shear force first. And shear force can be calculated by using this Newton's law of viscosity. And this tau is certainly is equals to F S divided by contact area. So this can be written like F as S is equals to mu, and du is the change in the velocity. So velocity over here we will write it as absolute velocity. Why we will write it as an absolute velocity over here? Since we know that this rod is moving, so the velocity of this rod is what? It is 4. Okay, and this outer rod is stationary, or cylindrical rod is stationary, hollow cylindrical rod is stationary. So it will be, the absolute velocity will be 4 minus 0 because it is stationary. So 4 minus 0 we will take into consideration, and we write it as a absolute velocity over here. So similarly we will write down the thickness of the fluid layer. So thickness of the fluid layer is basically, it is since the complete diameter is 10.06 and it is, the rod is 10 centimeters, so it is basically this minus this divided by 2, 0.03 centimeter on this side and 0.03 centimeters on the other side. So we'll put the values. Mu is the coefficient of friction, which mu is the viscosity which is given to us, which we will be calculating. So mu is the viscosity that has also also to be calculated for this. So Fs is equals to mu 4 by 0.03, T is equals to 0.03 centimeter, certainly converted to SI units, and it will be in meters. So pi d is what? D is the diameter. Again, it is converted into SI units, so it will be 0.1, and L is the length of the this rod. So it is 1 meter. So the shear force will be mu times 4186.66 newtons after calculating this. Now, by invoking the Newton's second law of motion, where we can say that the force is equals to mass into acceleration. So the force with which it is coming down will be equals to mass into acceleration. So what is the force basically? The force is basically the weight, because it is also a force, the weight minus the resisting force Fs. So 50 minus Fs will be equals to mass into acceleration. So 50 minus Fs is basically 50 minus mu into 4186.66 is equals to mass into acceleration. So mass is equals to W by G, because you know that we can write m is equals to W by G. Okay, so mass is W is basically 50, so 50 divided by 9.81, which is acceleration due to gravity, and A is the deceleration, because here it is retarding, deaccelerating, so it will be minus 0.5. So upon calculating you will get the dynamic viscosity of the fluid. So the dynamic viscosity of the fluid is 0.0125 Newton second per meter square. In the next part, we have to calculate the viscous resisting force. So viscous resisting force we will calculate by putting this value mu in this Fs. So what we will get, Fs is equals to mu into this. So we will get this the viscous resisting force Fs, which is to be calculated, is 52.33 Newton after calculation. So this is the first part of the numerical. So in the second case, we will be using again the Newtonian's law of viscosity. That is, since we have the fluid over here, we want to rotate this rod at 2500 RPM. So we will be using this formula once again. That is, your shear force is equals to mu u by t pi dl. That is, pi dl is your lateral surface area. In that case, the rod is at rest. Now what we have to do, In order to rotate this rod at 2500 rpm, the power is required to be calculated. So this green color over here is the lubricating oil fill. So we will find out the peripheral velocity first of all. What in this case, so peripheral velocity will be given by your formula pi dn by 60, and this after submission of the various values, that is diameter over here is 0.1 and meters. So we'll put these values over here and we'll get u as 13.08 meter per second. Similarly, we will try to find out omega, that is 2 pi n by 60, and again over here it's 2500. So we'll put the value over here and we'll get this omega as 261.66 radians per second. In this case, the rotation will be in this direction. As you know, if you want to rotate it, so it will be this case. It will not be the previous case wherein the sliding was in the linear direction, where because the box was this rod was sliding in the downward direction. So the shear force was certainly in the downward direction, but here the shear force will be in the tangential direction. So after getting these values, we'll put these values in this above equation, and we have calculated the viscosity of your oil in the previous case. The same viscosity of the oil will be used over here. Velocity we have calculated now, that is 13.08 will be used over here, and your thickness of the oil film, which is 0.03 centimeter, certainly it will be converted into meters, so we'll have this value over here, and pi, it's a constant, and d is the diameter again of this cylindrical rod, and l is the length of this rod. So this will give you the lateral surface area, or the surface area which will be in contact with the oil lubricating oil film and will be used to calculate the shear force. So after putting these values, we get the shear force as 171.13 newtons. So the frictional torque now can be calculated by using this formula, and basically the frictional torque will be equals to the viscous force multiplied by the radius. Okay, so the frictional torque will be equals to viscous force into radius. Viscous force we have, which we have calculated over here, that is the shear force 171.13 newtons multiplied by 0.05, that is your radius of your this particular rod, that is in basically in meters. So it will give you the torque as 8.55 newton meter. So the power utilized in overcoming this frictional resistance, rather the frictional resistance, or is the resistance which is basically due to the viscosity of the oil over here. So in order to rotate it at 2500 rpm, the power that will be utilized will be given by T into omega. T is your torque, omega is your angular velocity. So T is 8.55 Newton meter we have calculated over here. We'll put the value of T over here, and omega, it is 261.66 radians per second that we have already calculated, and after multiplication we'll get the power as 2237.19 watts. So certainly we can write the power in terms of the kilowatts, and it can be given as 2.237 or simply 2.24 kilowatts. So this will be the power that will be required under these given conditions to rotate this rod at an RPM of 2500 RPM. So the next problem is we have a box of 100 Newton which slides at a velocity of 20 meter per second due to oil lubrication between the box and the surface. The box is cubical in shape with side 20 centimeters. What we have to do, we have to calculate the thickness of the oil film, and it is given that the coefficient of friction between the box and the surface is 0.01 and viscosity of the oil is 1 poise. So the figure will be likewise this. So we have drawn the schematic of this problem. This will be a box, and blue color will be your
thickness of the lubricating film, where mu is your coefficient of viscosity of your oil film, and F is the coefficient of friction between the box and the surface. So we have to find out H. This box moves with a velocity v, which is 20 meters per second. So this is the given data we have. Weight 100 newtons, velocity 20 meter per second. Contact area 20 into 20, the area which will be in contact with the film. So 20 centimeter is the side of the cube. So 20 multiplied by 20 will give you the contact area, and it is equal to 0.04 meters square. Viscosity is in poise, and it will be converted into SI units, that is Newton second per meter square. And coefficient of friction is given likewise this. So we have to find out average film thickness, that is H. So we know that the frictional force or the tangential force that will act over here will be is equals to mu into n from the law of friction. So mu is your coefficient of friction, but here in that case we take into consideration F as the coefficient of friction. So it will be F over here, not mu. So F into normal reaction, that is your weight of the box. So F multiplied by this normal reaction will give you the frictional force or tangential force or the shear force. So it will be 10 newtons. So since we have the fluid over here, we can also use the Newton's law of viscosity, and by using the Newton's law of viscosity we can also find out the shear force or the tangential force over here, and that is equals to mu du by dy into A. So mu is the coefficient of viscosity over here, it is 0.1. Du is your velocity of the box, or you can write it as U, that is 20, and dy is the film thickness, oil film thickness, which is H over here. You can write H over there, and A is the contact area. So by equating the frictional force and the shear force, which is obtained by using the Newton's law of viscosity, we can work out the unknowns from this equation, and the unknown over here is H, and the value of H from this equation will be equals to 0.008 meters, or simply it is equals to 8 mm. So this was a small problem on the Newton's law of viscosity.
So coming on to the last problem of Newton's law of viscosity. So we have a flat plate weighing 300 newtons, which is to be moved in an upward direction at a constant velocity of 1.2 meter per second along a surface inclined at an angle of 45 degrees. The coefficient of friction between the surface and the plate is zero point 0.3. We have to calculate the magnitude of force that needs to be applied in the horizontal direction if the surface is lubricated with a fluid having viscosity of 0.02 Newton second per meter square and the layer thickness of the fluid is 0.5 mm, then we have to calculate the decrease in the required force. The effective area of the plate is 600 centimeter square. So basically we have to recognize the problem first. So let's draw a diagram. So what we can see is that this is a box which is required to be lifted with a velocity of this. We have to apply a force in the horizontal direction. That is, in the first case, we denote it by F1. So the surface is inclined at an angle of 45 degrees, and the weight of the box is 300 newtons. So we will have a reaction like this. So there will be a normal reaction, and this normal reaction uh, will be given by F and 1, and the angle is 45 degrees as an inclination, and the coefficient of friction will be noted by F, which will be equal to 0.3 in this case. So when you will try to apply a force on this, there will be a resisting force that is FF, which will be along this surface, and it is required to be moved with a velocity of 1.2 meter per second. So this is the given data. As I've told you, the contact area is important, which is 0.06 meter square, which is given to us. Viscosity is given. Layer thickness is also given, which will be utilized for the second case. Friction, coefficient of friction F is also given. So what we have to find out? We have to find out the magnitude of the force in the first case. That what amount of the force will be applied, so that we'll get a velocity of 1.2 meter per second in order when the block will be pushed in an upward direction. And In the second case, we have to find out the decrease in the required force, because in the second case, below this box, we will use a lubricating oil or lubricating film. So certainly there will be reduction in the force which will be required to move the box. So what decrease in the force will be there, that we have to calculate for the second case. This diagram is for the first case. So how we will move, what we will do, we will try to first of all, since by using the basic mechanics principle, we will try to use a summation principle wherein the forces in x direction, summation of the forces in x direction will be equals to 0, and the summation of the forces in y direction will also be equals to 0. Okay, so what we will do, we will resolve this fn1, and it has been resolved over here. We will resolve in this plane over here. This will take as x and this will take as y. So f1 will come in x direction. Okay, so and in x direction, what will come, this fn1 will also come. So fn1 will be in opposite direction. So f component of the fn1, and it is basically what component of fn1 will be fn1, yes, it will be fn1 sine of theta. So fn1 sine, it is 45. Okay, okay, one more thing will be there, that will be, if you will resolve this also. Okay, so what you will get, you will also get the component of the frictional force, that will also be in this direction, component of frictional force f, that will also be in this direction, since this angle will be 45 degrees. Okay, so it will be ff cos of 45. Okay, so these will be the forces which will be in the x direction, and similarly we will have the forces which will be in the y direction. Simply weight is in y direction. Okay, and the component of this force, that is this component, and we will call it as fn1 cos 45, that will be fn1 cos 45, that will be in this direction, and there will be another component, that is this one, it is ff. So we will have this component also which will be in the downward direction, that is ff sine of 45. So forces in y direction, summation of the forces in y direction will be 0, and summation of forces in x direction will be equals to 0. So we will use the summation of forces in x direction equals to 0, and summation of forces in y direction equals to 0. Accordingly, the forces in y direction will be given by this equation, where Fn1 is a normal reaction and Ff is the frictional force, and we'll put these values over here. And you know that Ff is the friction force, it is given by the coefficient of friction multiplied by your normal reaction, and the values will be, likewise this Ff is equals to F is equals to 0.3, and weight, as you know, is 300 newtons. So what we will get, we will get the Fn1, that is normal reaction over here, from this equation. So Fn1 is equals to 606 newtons. So we'll take into consideration the next case, that is summation of forces in x direction equals to 0. Similarly, we have an equation for this. So F1 is equals to minus Ff cos of 45 minus Fn1 sine 45 is equals to 0. So we'll try to put the value of this Fn1 over here in this equation, and we will try to find out the force, that is F1, in the first case, which is required to slide this box. So accordingly, Ff is equals to F into Fn1,
So Fn1 here is the value which is 606 newtons. After putting these values, we will get F1 is equals to 556.97 newtons. So this is a first case wherein the force required to slide this box is 556.97 newtons. So in the second case, what we have a lubricating film in between as given in the question. So this orange color is a lubricating film. So the force of friction now will be the shear force. And since we have used the lubricant over here, that force will now be due to the shear force, and Newton's law of viscosity will then be used to calculate the shear force. In the previous case, we were using the formula F is equals to mu n, or which over here is F is equals to F of n. So this was a formula which was used in the previous case in the dry conditions, but here we will use the formula, and that is your shear force, which will be given by Newton's law of viscosity. So we'll put the values of shear force, different values to get the shear force. Fs is equals to mu. Mu is your coefficient of dynamic viscosity, which is 0.02. Du is your velocity. We can put the absolute velocity of the box over here. So it is 1.2, and dy is the film thickness. It is 0.0005 meters, and multiplied by the area, that is area of the contact of this particular box. So the contact area of the box is 0.06. So after that we got the value of FSS 2.88 newtons. So again, we will use the similar case over here, which we used in the previous case. The summation of forces in y direction is equals to 0. So in that case, again, the same equation will be used. The difference will only be that in the previous case, we used FF. Here we will be using FS, because the force of resisting force is certainly due to the liquid film over here. So the second case is its second case, so we will use the subscript as 2. So we'll put the values of Fs over here in this equation, and Fn2 we will again try to find it out, and Fn2, the normal reaction 2, will be is equals to 427.26 after the summation of these values. So again we will use the summation of forces in x direction equals to 0 to find out the force, that is F2 over here. So the same equation is there, summation of forces in x direction equals to 0, but instead again we have Fs instead of Ff. We have Fs, that is force due to shear. So we will put the value of shear force over here, and we will put the value of this Fn2, which we have calculated over here for the second case. So these are the values over here. So after that we'll get, that is your F2, the force which is required to move the box in second case with a velocity of 1.2 meter per second in the upward direction, which is inclined to a plane at an inclination of 45 degrees. So this is the second force. So the second part of this particular numerical was to find out the decrease in the required force on after the application of the lubricating film. So certainly the force which was in the dry condition was 556.97. Here you can see that, and the force which is in the second case when the lubricating film has been used is uh, 304.11 newtons. So difference between these two forces will give you the decrease in the required force on the application of a lubricating oil or lubricating film having a viscosity of 0.02 Newton second per meter square. So the decrease in force is given by this formula, and it is equals to 252.86 newtons.
So these were the books which were referred during the course of action. Uh, these are the three books by St. Jalan Simpla, D.S. Kumar, S.K. Som and Viswas. So these books were referred during the course of action. So I thank you very much for watching this video on the numericals related to the Newton's law of viscosity, where we discussed three numericals on Newton's law of viscosity. And in the next video, which will be the last video of this chapter 1 on introduction to fluid mechanics. So in the next video, we will talk or we will discuss the numericals on capillarity and surface tension. Till then, I take your leave. Thank you very much.